To understand the structure of the Collatz conjecture, we can approach it in reverse. Instead of tracing numbers forward, we work backward through the inverse Syracuse map. Every unique sequence of halving operations a number undergoes is recorded as an exponent word, a precise symbolic history of its trajectory. We translate these operational histories into an exact mathematical framework using this specific affine inverse branch function. The variable m represents the exact length of the exponent word, the number of accelerated steps in the sequence. Up in the numerator, k tracks the total sum of all the individual exponents within that specific word, and c is a constant term, generated recursively from the exact sequence of halving operations we are tracking. Mapping the variables this way translates any operational history into a strict affine framework, creating a rigid arithmetic foundation for analyzing the conjecture. We must determine if two distinct operational histories can yield the exact same affine map. If two maps have equal slopes, the unique factorization of 2 and 3 requires that both their lengths m and their total exponent sums k be identical. That constraint narrows the entire problem of differentiating the maps down to a single parameter, the constant term c. To prove faithfulness, we need to mathematically determine if equal constants unconditionally force two exponent words to be identical, symbol by symbol. We start by assuming that two words, k and l, produce the exact same constant. As established, both words share an identical length, m. We decompose the first word, k, into its initial step, k1, and its remaining suffix, k'. We apply the same decomposition to the second word, l. Substituting the c variables with their recursive identities expands the equation. A shared term now appears on both sides of the expansion. We subtract this term from both sides. This leaves the equation in a condensed state. Stripping away that additive term isolates the base 2 exponents, allowing us to begin the extraction phase. To solve this, we now introduce our primary analytical tool, the two-adic valuation operator, v2. The v2 operator extracts the highest power of 2 that divides an integer. For the operator to cleanly pull out the exponents k1 and l1, we must first ensure the suffix constants do not contain any additional base 2 factors. We look to a foundational parity rule. The constant term for any non-empty exponent word is strictly odd. Since the constants are strictly odd, their two-adic valuation is 0. The operator ignores the constants entirely, focusing only on the powers of 2. We execute the valuation. Because the odd suffix constants contribute nothing to the base 2 extraction, we dismiss them. The operator pulls down only the exponents. This proves the first operational halving steps of both words are mathematically identical. We return to the earlier equation and divide both sides by the verified equal 2 to the k sub 1 terms. This recovery returns us to the starting hypothesis, but now it applies to the strictly shorter suffix words. Applying this logic recursively, stage by stage, extracts and matches every subsequent exponent until we reach the empty word. This iterative descent forces the words to match symbol by symbol, proving that word k must equal word l. This sequence constitutes a complete unconditional proof of faithfulness across the entire formal exponent word semigroup. This streamlined methodology requires no multi-stage peeling of terminal blocks. Because the odd parity rule carries the analytical weight at every stage, we avoid the need for separately tracked modulus shifts. Every unique exponent history maintains its own distinct identity, making structural collisions within this system impossible. We can now return the focus from the formal semigroup to genuine, admissible Syracuse itineraries. In this architecture, every admissible finite Syracuse itinerary maps directly to a unique residue class modulo 3 to the m. This mapping establishes the arithmetic infrastructure required to isolate individual itineraries before searching for cycles. It ensures that no two different symbolic histories are ever identified as the same representation when solving the cycle equation. With collisions mathematically excluded, we have the rigorous foundation needed to address the precise divisibility conditions of genuine Collatz cycles.